Have you ever found yourself wondering how computers handle math problems that are just way too big for a regular calculator? Well, today we're going to dive into a classic coding challenge that does exactly that. We're talking about adding numbers so massive they have to be treated like text. I mean, just look at these things. Each one is 20 digits long. Your typical integer type in most programming languages, it's just going to overflow. It can't handle it. So if you can't actually treat them like numbers, how in the world do you add them together? That's the puzzle we're solving today. And this brings us to a really popular problem you'll see on sites like LeetCode. It's called add strings. The idea sounds simple. You get two numbers as strings of text, and you have to return their sum also as a string. But as you're about to see, the real fun is in the details. Okay, let's make this real with a few examples. If you get 11 and 123, the output should be 134. Makes sense. 456 plus 77 should give you 533. And of course, 0 plus 0 is just 0. These look easy, but the trick is you can't just convert them to numbers and hit the plus button. And here's what makes it a real brain teaser. These are the rules of the game. First off, no using any special libraries that are built to handle huge numbers. That's cheating. Second, you are explicitly forbidden from converting the strings to integers directly. This forces us to really think about what addition is, and with numbers that can be up to 10,000 digits long, we definitely need a solid plan. So, what's the plan? Since the computer's built-in math is off-limits, we basically have to teach it how to do addition from square one. And it turns out, the absolute best way to do that is to copy a method that every single one of us learned as a kid. And here it is, the big aha moment. The solution isn't some crazy, complex computer science algorithm. It's literally just grade school math. We are going to build a program that does exactly what you used to do with a pencil and paper, adding numbers one column at a time. It's a beautiful insight that makes this scary problem feel totally manageable. Come on, you remember this, right? You line up the numbers on the right, you add up that first column of digits, you write down the ones place, and you carry the 10 over. Then you just slide over to the next column and do it all again, making sure to add in whatever you carried. That's it. That's our blueprint. So how do we get a computer to follow that blueprint? For this, we'll use a classic programming pattern called the two pointers technique. You can literally think of these pointers as your two index fingers, pointing at the digits in each number that you're about to add up. So what exactly is this two pointers thing? It's a really simple but powerful idea. We're going to create two markers, or pointers, that each keep track of our position in one of the number strings. We'll start them at the very end of each string, and then we'll walk them backward, right to left, one step at a time, just like we would on paper. Okay, let's get our hands dirty and actually walk through our example, adding 456 and 77. Here's our starting setup. We've got one pointer at the 6 and 456, and another at the last 7 and 77. We also need a variable to keep track of our carry, which starts at 0, and an empty string for our final result. All right, first step. We add the numbers at our pointers, so 6 plus 7. And we can't forget to add our carry, which is 0 right now. That gives us a grand total of 13. The question is, what do we do with that 13? Just like in school, the units digit, which is the 3, gets put into our result string. The tens digit, the 1, becomes our new carry value for the next round. And finally, we move both of our pointers one step to the left, getting them ready for the next column. On to the next column. Now our pointers are on the 5 and the other 7. So we add 5 plus 7, but this time we have to remember to add that carry of 1 from the last step. And what do you know? We get 13 all over again. And we just rinse and repeat. The units digit 3 gets added to the front of our result, so now our result is 33. The tens digit 1 becomes the new carry. And again, the pointers both move one step to the left. See how that result string is building up? Okay, now for a really important detail. What happens when one number runs out of digits? See, the pointer for 77 has now gone past the beginning of the string. Our algorithm has to be smart enough to just treat that missing digit as a 0. So our calculation becomes 4 plus 0 plus our carry of 1, which equals 5. This time, our sum is just 5. So we add that 5 to the front of our result string, which now says 335. Since 5 is a single digit, the new carry is 0. Now, both of our pointers are done, and our carry is 0. That means the loop is finished.
So we're basically done. We've processed all the digits, we've handled the carry, and we have a result string. But if you look closely at what we've built, you'll notice something isn't quite right. There's one final really clever twist we need to take care of.
And here's the big reveal of that twist. Our algorithm gave us 335. But we all know from the start that 456 plus 77 is 533. It seems like we did everything right, but our answer is perfectly, completely backward.
So what gives? Why did that happen? Just take a second and think about the process we just went through, step by step. Where in our logic did we accidentally introduce this reversal?
The answer is actually pretty simple and elegant. We built our sum from right to left. The very first digit we calculated, that first 3, was the last digit of the true answer, but it was the first thing we put into our result string, so of course it's backward. All we have to do is flip it. And this is exactly what the official solution says to do. The very last step, after the loop is all done, is to just take that string we so carefully built and reverse it. That one simple operation gets us from 335 to the correct answer, 533. All right, let's wrap this all up. We took a problem that looked really complex, but we realized the solution was as simple as grade school math. We used the 2 pointers technique to imitate what we do on paper, and we remembered to handle that one final reversal to get the right answer.
And what's really cool is that this solution isn't just clever, it's also incredibly efficient. The time it takes to run is directly related to the length of the longer number. We just make one single pass through the digits, and it uses a tiny, constant amount of extra memory, just enough for our pointers and the carry, no matter if the numbers are 10 digits or 10,000 digits long.
So there you have it. We've mastered adding numbers of any size. But this kind of opens up a whole new can of worms, doesn't it? It's awesome that we can add, but what would it take to subtract them? How would you handle borrowing instead of carrying? That's a fantastic puzzle